assistant professor in mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss Lagrangian formulations, and in Lagrangian formulation from classical mechanics, point is conservation of energy. Example for conservation of energy show that total energy of a particle moving in a conservative force field remains constant if the potential energy is not an explicit function of time. For the solution, we suppose our assumptions let a particle of mass m be moving in the conservative field of force f. Let r be the position vector of the particle at an instant. Then the total energy of the particle is E is equal to T plus V, where T is the kinetic energy and V is the potential energy. Differentiating with respect to T, therefore dE by dt is equal to dt by dt plus dV by dt. When the force F is equal to m dV by dt, therefore F dr is equal to F dV by dt multiply dr by dt multiply t dt. F dr is equal to m v dv, therefore m dr f dr is equal to d by derivative of 1 by 2 mv square, and f dr is equal to dt, therefore f dr by dt is equal to dt by dt. Derivative of kinetic energy with respect to time t. Similarly, we have the potential energy V is equal to V of RT. Therefore, dV is equal to differentiating dou V by dou x dx plus dou V by dou y dy plus dou V by dou z dz plus dou V by dou t dt. dV is equal to del V dr plus dou V by dou t dt. dV by dt is equal to del V dr by dt plus dou V by dou t. Substituting this d by dt, therefore d by dt is equal to f dr by dt plus del V dr by dt plus dv by dt, and dE by dt is equal to f plus del V dr by dt plus dou V by dt and dou t. Since f is conservative, therefore f is equal to minus del V, therefore dE by dt is equal to dou V by dou t. Therefore now if the potential energy V is independent of time t, then dE by dt is equal to 0, therefore E is conserved, therefore total energy of the conservative field is conserved. If the force acting on a particle, theorem, if the force acting on a particle is conservative, then show that total energy is conserved. For solutions for proof, we consider the particle is acted upon by the force F. Then if it moves from position P1 to P2, hence the work done by the force is given by W is equal to work done is equal to integral from R1 to R2 P1 to P2 F dr, here where F is equal to F dr by dt. F is equal to P bar dot is equal to m dv by dt Therefore, W is equal to integral from P1 to P2 f dv by dt dr by dt into dt is equal to integral from P1 to P2 f dv by dt v dt and is equal to integral from P1 to P2 one derivative of 1 by 2 mv square with respect to t dt and integrate 1 by 2 mv square P1 to P2 and 1 by 2 mvt square minus 1 by 2 mv1 square, and that is W is equal to T2 minus T1. Now if the force F is conservative, then it is derivable from a scalar potential function V, which is functions of position only. Therefore we have F is equal to minus del V is equal to minus del by V del bar where V is the potential energy. Substituting the value in equation 1, we get W is equal to uh, minus integral from P1 to P2 dou V by dou R dr is equal to minus integral from P1 to P2 dV is equal to integrating minus V from P1 to P2 and W is equal to V1 minus V2. Here W is equal to T2 minus T1 and here W is equal to V1 minus V2. Then T2 minus T1 is equal to V1 minus V2. Therefore T2 T1 plus V1 is equal to T2 plus V2 is equal to constant. T plus V is equal to constant. This shows that total energy of the particle is conserved. Alternative method, the force is conservative, therefore F bar is equal to minus del V, where V is the potential energy and Newton's second law of motions define the force by F bar is equal to mr dot. Therefore mr double dot is equal to minus dou V by dou R, differentiating with respect to R dot, mr double dot R dot dou V by dou R dot d by dt of 1 by 2 mr dot square plus V is equal to 0, integrating 1 by 2 mr dot square plus V is equal to constant. This shows that total energy of the particle moving in the conservative field of force is constant. Therefore, total energy is conserved. Next one theorem. If the energy and external and internal forces are both conservative, then show that the total potential energy V of the system is given by V is equal to summation of VIE plus 1 by 2 summation of VIJ internal over IJ, where VIE is the potential energy arises due to the external force FI and VIJ internal is the internal energy arises due to the internal force FJ internal. Further show that the total energy of the system is conserved. Here two types of forces, external and internal forces, are acting on the system of particle. To find the total energy of the system, we find the work done by all the forces, external as well as internal, in moving the system from initial configuration 1 to the final configuration 2. It is given by W is equal to summation of integral from first configuration to final configuration f by dr by dri bar, where f I bar is equal to f I of b plus fj internal. Therefore W is equal to into summation of I integration from 1 to 2 fi bar dri bar plus in summation of integration from 1 to 2 fj internal dri bar. Let fi bar be conservative, then there exists a potential VIE such that fi is equal to minus del I VIE is equal to minus dou VIE by dou Ri bar. Therefore, summation of integral from 1 to 2 fi dri bar is equal to minus integral from 1 to 2 dou v by I of e by dou Ri dri bar is equal to minus integration from 1 to 2 dvie. Therefore, integration from 1 to 2 summation fi dri bar is equal to minus summation of VIE 1 to 2. Now consider the second term on the RHS. Therefore, summation of Ij integral from 1 to 2 fj internal dri bar is equal to integration from 1 to 2 fj internal dri bar interchanging I and j on the RHS. Therefore, fj internal is equal to fj internal dri bar 1 to 2 integration from fj internal dri bar is equal to minus fj internal dri bar for fj internal is equal to minus fij internal. Therefore, adding these equations, we get into summation of ij integral from 1 to 2 fj internal dri bar is equal to 1 by 2 summation of ij integral from 1 to 2 fj internal dri minus drj and this is equal to drj bar. If the internal forces fj internal are conservative, then there exists a potential Vij internal such that fj internal is equal to minus del ij Vij internal is equal to minus dou Vij internal by dou Rij bar. If Vij there is the gradient of with respect to Rij, then thus the above equation becomes fj internal dri bar integral from 1 to 2 is equal to minus 1 by 2 integral from 1 to 2 dou v by dou vij internal by dou rij drij bar, and fj internal dri bar is equal to minus 1 by 2 integral from 1 to 2 dou v dvij internal. Therefore, integral from 1 to 2 fij internal fj internal dri bar is equal to minus 1 to 2 vij internal 1 to 2. Therefore, this is equal to v1 minus v2, that is v is equal to vie plus 1 by 2 vij internal represent the total potential energy of the system or particle. Similarly, the total work done by the force on the system in terms of kinetic energy is given by W is equal to integral from 1 to 2 f I bar dr d by dt of m mi vi dri by dt m dvi by dt vi dt. Therefore d derivative of 1 by 2 mi vi square and is equal to t2 plus t1, and this is t1 plus v1 is equal to t2 plus v2, and this shows that total energy of the system of particle is conserved.